Hello everyone and welcome back to the series of Digital Logic Design. Today we will study about the magnitude comparator. The comparison of two numbers is an operation which determines whether the one number is greater, lesser or equal to the another number. Now corresponding to this, a magnitude comparator is a combinational circuit that compares two numbers like A and B and determines their relative magnitudes. The outcome of this comparison is specified by three binary variables, and each binary variable indicates that A is greater than B, equal to B, or less than B. Now for designing a comparator circuit, we will use an algorithm because one may suspect that a comparator circuit possesses a certain amount of regularity. Now, the digital functions that possesses an inherent well-defined regularity can be usually designed by means of an algorithm, a procedure which specifies the finite steps that, if followed, give the solution of the problem. Now we will start with a 1-bit magnitude comparator circuit. For instance, we have two 1-bit numbers like A and B which are being compared. So we have three possibilities that A is greater than B, or equal to B, and can be less than B. Now here, for comparison purpose, we will use the following circuit. The circuit uses exclusive NOR gate which determines equality of two bits. And if two bits are equal, either having a value of 0 or 1, it will give answer of 1, otherwise 0. And if A is greater than B, the logic implies that A dot B prime will give answer 1. Because if B have a value of 0 and A have a value of 1, then B prime will be equal to 1. And 1 dot 1 will indicate that A is greater than B. And if A is less than B, then we will use algorithm that A prime dot B will be equal to 1, because if A is less than B, then A must have a value of 0. So A prime will be equal to 1 and 1 dot 1 will indicate that A is lesser than B. The function table for 1-bit magnitude comparator is also given here. Now after 1-bit comparator, we will study a circuit which will make comparison of two 4-bit numbers. Consider we have two numbers A and B which consist of 4 digits, and we will write coefficient of each digit in descending order, like A will be equal to A3, A2, A1, A0, and B will be equal to B3, B2, B1 and B0. Here each subscripted letter represents one digit or one bit in the given numbers. Now the two numbers are equal if all the pairs of the significant digits or the significant bits are equal, like A3 must be equal to B3, A2 must be equal to B2, A1 must be equal to B1, and finally A0 must be equal to B0. If these equalities are valid, then the two given numbers are equal. Now if the given numbers are binary, then these bits can either have a value of 1 or 0, and the equality of each pair of bits can be expressed logically with an exclusive NOR function such as xi will be equal to ai dot bi plus ai prime dot bi prime. Here xi is a binary variable which represents equality of each bit and is equal to exclusive NOR function of 2 bits, where the variable I can have a value from 0 to 3. Now if xi equals to 1 only if the pair of bits in the position I are equal. Here the both bits can be 0 or 1. The equality of two numbers A and B is displayed in a combinational circuit by an output binary variable we designate by the symbol A equals to B. This binary variable is equal to 1 if the input numbers A and B are equal and is 0 otherwise. Now for the equality to exist, all the xi variables must be equal to 1, and this is dictated by a condition of an AND operation of all variable. That is, the binary variable a equals to b will be equal to the product of x3, x2, x1 and x0. The binary variable a equals to b is equal to 1 if all the pairs of digit of the two numbers are equal. Now to determine latter two cases, which are a is greater than b or less than b, we inspect the relative magnitude of pairs of significant digit starting from the most significant position. If the two digits of a pair are equal, we compare the next lower significant pair of digit, and this comparison continues until a pair of unequal digits is reached. Like if the corresponding digit of a is 1 and that of b is 0, we must have a greater than b. And if the corresponding digit of a is 0 while that of b is 1, then we will have a less than b. Now the sequential comparison can be expressed logically by the two Boolean functions. As said earlier that this comparison starts from the most significant bit, so the binary variable a greater than b will be indicated by the given equation. And similarly, if we are calculating a less than b, then the binary variable a less than b is indicated by the second equation. Here, important thing to note is that if we are calculating a greater than b, then all the sum of product terms in equation a will have bits of b in the prime form, like b3 prime, b2 prime, b1 prime and b0 prime. And if we are calculating a less than b, then all the bits of a will occur in second equation in the prime form, like a3 prime, a2 prime, a1 prime and a0 prime. The symbols a greater than b and a less than b are the output of binary variables that are equal to 1 when a is greater than b and a is less than b respectively. Now here the figure represents the gate implementation of three output variables just derived is simpler than it seems because it involves a certain amount of repetition. The unequal outputs can be used the same gate that are needed to generate the equal output. Like here, the exclusive NOR gate is not used directly, whether the same operation of exclusive NOR gate is implemented in the form of equation. And the portion of this equation in gate implementation is used in the calculation of unequal cases. And the logic diagram of 4-bit magnitude comparator is shown in the figure. Thanks for watching the video and stay connected for more interesting videos.